Okay, this is section 4.0, and this is example 4.0.2, and it's kind of weird how they just stuck this in here. I don't really feel it follows from what they've been doing. Now, earlier we did look at finding the area of a triangle, and that had to do with points. But yeah, I don't know, but it's an interesting example, just in that it is a neat thing to know. So I've got 2 points out here in the XY plane, X1, Y1, and X2, Y2. So I have these 2 points, and they are distinct. So if these are distinct points, then the line through P1 and P2 has equation, and so you can set up that equation using a determinant, and so that's just kind of an interesting interpretation again of a determinant. So here's x1, y1 and 1, and then x2, y2 and 1. So I take that determinant and set it equal to 0, and I ask, well, what x and y would make this 0? Well, if we take that determinant, then, and we expand by the first row, right, we have that x times our minor determinant there, so that'd be y1 minus y2, okay, because I took y1 times 1 minus y2 times 1, so that's kind of cool, right? And then minus x, minus y times that minor, and so I've got an x1 minus x2 there, and then plus 1 times, and I have what, x1 y2 minus y1 x2, and that all equals 0. Okay, so what the heck happened with this, right? So we do this, and you can write this as, if I solve for y, right, I get y, well, let me leave the x1 minus x2 here for a moment, equals, and so I took it to the right side of the equal sign, you can think of it that way, and then I have y1 minus y2 times x, and then plus x1 y2 minus y1 x2. And so this is y equals y1 minus y2 over x1 minus x2 times x, and plus x1 y2 minus y1 x2 over x1 minus x2. Okay, now, here's where I think, you have to, think about this a little bit. Now, their argument simply is that when I wrote this down, I had certainly a line, right? Because this would be, some A, some B, and some C, and that would be AX plus or minus, whatever I want to call it, by, and then plus C equals 0. Okay, that's definitely a straight line. And then their proof is, and this is, okay, yeah, I hadn't really thought about that with their proof. Okay, now I see why they threw that in. Okay, I'm a little slow. The reason they threw this in is then it is obvious, I say obvious, that x1 and x1 y1 and x2 y2 are on this line, because that's the real question. Because if I put x equals x1 and y equal y1 up here, then I have a matrix with two rows the same, and so that will satisfy a determinant of 0. Okay, so I don't necessarily even have to here. I could substitute in my x1, my x equals x1 and my y equals y1 and show that I get 0. But we know from theorem 4.0 and I think that was 6, we know from that theorem, yes, that if I have two lines the same, then I do get a determinant of 0. So it does happen that if x is x1 and y is y1, we get 0 for our equation. So that worked, and similarly for x2, y2. Okay? But, so you see then, though also just kind of solving this, that, sure, there's the right slope. Now, we need to do a little work on all this to say get the point slope form. I'm not going to do that. I'm going to use our proof, our linear algebra proof from theorem 4.06, but you can kind of see where it's heading, right? So the slope is fine, and here I can do some algebra on this, and I can get this whole thing into a point slope form, okay? Which would then, for us, be very recognizable that yes, x1 and y1 and then x2, y2 are on this line, okay? But we know this equality works for x1, y1 and x2, y2 because of theorem 4.06. So there's a nifty example, and they extend it in their comments. They say, if you take any number of points, n points in n-dimensional space, you can do this to create the equation of a plane or a hyperplane, and so this does extend, this idea does extend. So that's pretty nifty. So there's example, I think it was 4.0.2.